This is CPE 133. This is experiment 13. And what we're going to do in this experiment is implement a 6-bit multiplier. So it's essentially going to take two operands, multiply them together, and output the result. And this circuit is going to be controlled by a state machine. No surprise there. The objectives are to implement essentially a non-trivial algorithm in hardware. Now this is something you've been doing since 3rd grade, probably, long division, but now we're going to design a circuit that's going to do it for you. And particularly another objective in here is to use a shift register in your circuit. So this is a 6-bit multiplier. There's lots of multiplication algorithms out there. We're going to use typical long multiplication algorithm, which is something you're familiar with. And like I said, it's something you've been doing this for a long time, but implementing it in hardware is going to be a little bit different. It's going to be finite state machine controlled, of course, and for this experiment you're allowed to visually verify the proper operation. So this is a 3-bit multiplier example. Once again, many different algorithms to do multiplication with, but we are using this one. And so this is, I don't know, adding and shifting, blah blah blah. That's kind of what you've been used to for all this time, and it's no different than anything you've always done before. It's just using binary. So this is an example in binary. So what it's doing is multiplying 0 times this times this times this, and this is the result. And now I'm going to multiply, I'm going to erase this, 1 times this, this, and this, and here's the result. And essentially it's binary multiplication. It's an issue of 0 times 0, which is 0, 1 times 0, which is 0, or 1 times 1, which is 1. So what we're going to do here is get these, and when we do it longhand, we're going to get these 3 values, we're going to add them up, and we're going to come up with this answer like this. But in real life, particularly our adders only add 2 operands at a time. We can't really do 3 operands at a time. So we're going to do it a step by step in here, which we're going to use an accumulator for. So this, once again, is a 3-bit example. What we're going to use in this experiment is a 6-bit number, 2 6-bit numbers. So use the specified algorithm. This design cries out for an accumulator to store your results. Remember, we can only add 2 things at a time, which is the running total plus the new shifted value. So obviously there's going to be a shift register in here. You'll see that depending on how you do it, you may use 2 shift registers. Use the 7-segment display to display your results. By all means, we want to see this work, so use the clock divider in there so you can see the steps along the way. And lastly, you may want to throw in a extra LED in there just to show you visually which state you're in. That's optional. That's not really part of the experiment. Design this on paper first. Certainly you want to design your circuit and then generate a state diagram for your state machine that's going to control this circuit. And so this is really important. You have 2 different options here. I've said all along not to put data inputs into the state machine, but for this experiment you're allowed to do this. So that's going to generate a state machine that's going to require a state machine with about 7 states. It's okay to do for this experiment, but by all means you're allowed to use a right shifting shift register for one of the operands. Now if you look at the result, if you look at the example, it's obviously there's a left shifting shift register, but if you know what you're doing, and you're welcome to ask me about it, you're welcome to use a right shifting shift register for the other operand, or input that data of that operand into the FSM for the other option. So if you do the right shifting shift register option, you can do this thing in 2 states, and not a big deal on that one. So a couple other notes in the lab manual, be sure to check those out also.